Let's now consider the analysis of a multi-stage sampling design. So we have applied multi-stage sampling. How do we come up with estimators? Well, unfortunately, it is a little more difficult in terms of algebra when it comes to multi-stage sampling, and that is with stratification. You basically take your sample, your population to begin with, you split it into 2, or in the Belgian Health Interview Surveys case in 12 strata, and the first thing you do is you do everything that you would do with simple random sampling in every one of the strata separately, and then there are combination rules to bring it together. That's already more complex than simple random sampling, but it's overseeable. Here, though, we may have not just 12 sample fractions, we may have as many sample fractions as we have primary sampling units, and they can follow all sorts of rules. They can be constant, they can be proportional, they can go all over the place. So, what we will do is we will give some hints of how it works when we have, for example, 2 levels, primary and secondary sampling units, but keep in mind that you don't need to do all of this by hand, of course. It's nicely implemented in most software packages. Quantities can be estimated within a primary sampling unit, for example, within a town, and it's not that you can do it, you actually have to do it, even if you're not interested in it, because they're a vehicle to get to the entire population, which is the second goal. As I said, the expressions depend on the method that you use. For example, with self-weighting, at the second level, the sample fractions are constant. The F2i's are actually just F2. In simple cluster sampling, we go one step further, and they're equal to 1. And then things are a little simpler, but that's not always what we do. So, if we estimate a total based on multi-stage sampling, we have the total estimated from a secondary sampling unit. And I'm assuming equal selection probabilities within those. Even that can be changed. But I calculate a total, say, of all 50 people selected in a town, and then I scale it up from the 4 people that I've selected to the 50 people in the town. That's the factor up front. And then for the population total, well, for the population total, what I do is I take the previous quantities, I sum them over all of my primary sampling units, and then I say, yeah, but I selected 10 towns out of 30 towns. Okay, then I have to multiply by 30 divided by 10, I scale it up by a factor 3. And then once I have that, in the self-weighting case or in the simple cluster case, I can simplify matters a little bit. My formulas would indeed simplify. Clearly, no need to know these families by heart. Just know that they're there and that the software packages do implement them properly indeed. Okay, but that's for point estimates. We still need variability. How do we do that? Well, I'll also here present it for totals, knowing that for averages it's all the same, but you divide by 1 over n square. I will do it not for the most general case, because that would take us too far. So the cluster expression is a simple case of the self-weighted expression, which in itself is a special case of the most general case. But for non-self-weighted samples, it is a bit more complicated. So, like always, we have the calculated variance. If we would have a helicopter view over the population and we would know everything that we need to know on the entire population. One, but of course, in practice, we would estimate the quantities from a sample. Well, we can look at left and right. It's very equivalent in terms of algebra. But of course, what we can do in practice is only the estimated side. We have variability at the first level, and we have variability at the second level. So variability at the first level is how does a total in a primary sampling unit in a town, say, how does it vary around the town, the average across the town? And then at the second level, this is unit per unit. So it's the two levels of variability, the between town variability and the within town variability. That's at the population level. In a self-weighted sample, the actual variability is made up of, guess what, within and between variability, with finite population corrections associated to it, and then corrections for the actual sample sizes that we use. For simple cluster analysis, it's a special case because the second level variability drops off, isn't there. If there's no variability, there is no term describing it. All right, so let's look at the artificial population again. So we have already studied quite a few things. We have studied the intra-cluster correlations for simple random sampling, for systematic sampling based on several lists, and for stratification. Now, given what we said before, the lists from systematic sampling and the three clustering methods kind of come together here. We see that the impact on the precision is also the same. So the first clustering method would lead to an increased precision, which is somewhat unusual. The second one would lead to a decreased precision. Survey time. So there is the list based on x as an auxiliary variable and based on the strange z as an auxiliary variable. So let's look at the first one. The population is, we consider stratifications actually already based on x and z. But now we go further and say, let's define clusters in this way. 4 clusters. And we select samples of size 2, which is that we select a single cluster. Since there are 4 clusters, there are 4 samples possible in every case. And that's what they are. 1, 2, 3, 4, 5, 6, 7, 8. So in the clustered columns, you're not going to have 28 options, you're going to have only 4. And what we see at the end is that the variance increases from 144 to 320. And for that second clustering, which was based on the newspapers, which typically would lead to a decreased precision, now increases it because it actually, because clusters are so heterogeneous, it actually works in favor of precision, but that's not usually what you find in the field. If you say we look at towns, then towns is something that's, or families, something that's going to be much more similar to what we have here. 2 or 3 units that are not necessarily identical, but at least that are reasonably similar. And so the typical behavior of clustering is an increased precision. The artificial example and survey town and all are extreme in the sense that the effects are really magnified. They're much bigger than you would find in realistic samples. But that is indeed the effect that you may see happen. Here is the calculations behind it to see how we get to these numbers, of course, to the 320. They're still unbiased, that's no problem at all, so we don't worry there. Okay. Let's calculate the intra-cluster correlation. We can do that now and say our population consists of 4 possible clusters, at least if we base everything on x. On z, 4 possible clusters, but different ones. Okay. Good. Now, what are the correlations? Based on x, 0.904. That's an extremely large correlation, and that's not good news, but that of course explains why we go all the way to 320. If we base it on z, we go down to minus 0.71, and that means decreased variance, increased precision. So in the grand scheme of things, simple random sampling with replacement, that's the one producing 0 correlation. It's only one of the clusterings that get to such a high values. All the others are negative, with still systematic sampling with list Z winning, etc. Well, one thing we should not draw from this is general knowledge as to what is the ordering of the methods in any possible examples. No. It's an artificial example. It should not be carried too much forward, but it gives the connection between heterogeneity of the samples, which is the mirror image of the heterogeneity in the population. For example, if strata are very similar, stratification will lead to very dissimilar units in the sample because you sample from different strata. If people in the strata are the same but very different between strata, you take a few from all and you make sure that you span the entire range. So that will lead to negative correlation, and then you will end up somewhere here in the good region. The more negative the correlation, the smaller the variance of the estimator, and vice versa. And to top it off, what about the Belgian Health Interview Survey? Well, in the Belgian Health Interview Survey, we're going to do the same thing now, and we say we are going to use proc survey means, but we now take clustering into account, household clustering. So what does it give? Like always, it gives us, and I look forward a little bit, estimates for Belgium, and then estimates for the domains, which is Brussels, Flanders, and Wallonia separately. We still seem to get the same point estimates, but something may have changed in the precision. But before we go there, it's good to notice that there is actually three-stage sampling here. But in some packages, not in all, it's not possible to take all of the levels into account. So that's why we have household clustering the deepest level. If you take clustering at town level only, you pretend that individuals within towns are further independent. That's not true. So that's a fundamental mistake. If you go to the deepest level, which usually is the highest correlation, you expect, by the way, more correlation in people coming from the same household than in people coming from the same town. And even if there is some correlation at the town level, it will drop down on the household correlation. So in other words, if you estimate the household correlation to be 0.17, maybe it's only 0.15 because there is a small contribution from the town that has fallen upon the lower level. Okay, good. So where are we now? If we look at stable GP, for example, let's do that here. We see still the same point estimate, and eventually that needs to change a little bit with weighting. Well, if you look at the gray print, you do see that that happens, but the variance has increased. So by taking clustering into account, we properly see something for the first time happening, that is by an amount of 75% or even sometimes a bit more, so 25%, sorry, the variance is increasing because we do take the clustering and the resulting decreased precision from that into account. All right. So, you do see also that the effect of clustering is different for variable to variable. So there's no such thing like a common effect of clustering on all of the variables. No, stable GP may well be a family-related decision, whereas body mass index, yeah, there may be genetic features, etc. playing, but there is also a strong individual component. So even though members of a household may cluster, that clustering may be negligible in some variables and may be very high in other variables. There is no such thing like a uniform correction for clustering. No, you need to do it variable by variable. And then in section 17.6, we will discuss sample size determination. Now, sample size determination, general expressions are really complicated. Unlike before, where we at least could present formulas, not to learn by heart, but to get an idea, to build up some intuition also. Here, we really should say we rely on statistical software, on dedicated design software for survey methodology to do the calculations for us. So here are a few situations, the number of primary sampling units. If you have sampling in a self-weighted fashion the number of primary sampling units that you would select for a total, for an average, and so on. Okay. That brings us to the end of the chapter, not yet to the entire end of the part on multi-state sampling. There's a little bit more to come in chapter 18.